We know of thousands of exoplanets, and we're discovering more and more every day, thanks to some incredible missions like Kepler and TESS, as well as Earth-based planet hunting missions. And yet, for all of these worlds that we know of so far, we don't know of an Earth-sized world orbiting around a sun-like star in the habitable zone. We haven't found Earth 2.0. And the great hope was that Kepler would be the mission that found it. But too early on in the mission, its reaction wheels broke and they had to change the way the mission worked. They're still able to recover an amazing amount of science, but they didn't find that other Earth. And so now the mantle, the hope, the dreams move to the Plato mission from the European Space Agency. It's due to launch in 2026, and it will be doing something similar to what Kepler did, but also similar to what the TESS mission is doing. And over the course of its 4-year mission, it's expected to find probably a dozen Earth-sized worlds orbiting around sun-like stars. And so unless something really weird happens, Plato will be the mission that finds that Earth 2.0. When is it going to find it? Well, that is the topic of today's conversation, and I am talking with Dr. David Brown from the Plato Science Office. He's working with the scientists who are going to be analyzing the data coming back from Plato. And it's very interesting because they're actually not just going to be waiting for future transits. They're going to be studying the kinds of transits that happen and then already learn as much as they can in preparation for when that next transit does happen, so they can really confirm if they found that other Earth. It's a fascinating conversation, not just about the history of planet hunting, as well as the capabilities and how Plato is going to work and what the expectations are. And then, of course, we talk about the future and some interesting ideas for missions that could take Plato even farther. So enjoy this conversation with Dr. David Brown. David, now, I'm not sure if you were directly involved in this, but, as a person who's been looking at exoplanets for a long time, what was it like to be in the field when you all realized that Kepler wasn't going to find us that other Earth?
Oh, it was a bit disappointing, to be honest.
A bit.
Yeah. We'd sort of spent so long thinking about Kepler as almost as something it wasn't really designed to be, which was an Earth 2.0 hunter. And when we realized that almost certainly wasn't going to happen, even sort of vaguely, it was really disappointing, actually.
It was, and it's weird because we're here. I don't know how many years after Kepler launched. We were 1995 first exoplanet around a star, sun-like star, and so we are 30 years since that discovery, and yet we still haven't found that Earth-sized world orbiting around a sun-like star. And Kepler could have done it, and its loss was just this. I don't know. It was just this giant gap in the process. I mean, how far? I mean, did some amazing science, but how far did it kind of set us back, do you think?
I think, although it was disappointing when we realized it wasn't going to find another Earth, I think that realization sort of came in two stages. There was the bit sort of partway through the mission when we realized that even with the limitations of being able to follow up any of Kepler's discoveries or most of Kepler's discoveries, even with those limitations, we probably weren't going to get a second Earth from Kepler. So that was sort of part one of the realization, but there was still a chance we could push towards it really, really well. And then the second part of the realization, when Kepler broke, was sort of the not a sort of a complete disaster, because we'd sort of been expecting it to happen at any moment. And I don't think it set us back as much as it might appear from the outside. I think by that point, TESS was well underway to being a going mission. People were starting to think about improvements that could be made, and had been thinking about improvements that could be made to our data processing and our analysis and all these sort of things that go into finding that second Earth. They'd been thinking about them for the second half of the Kepler mission, really, or all the way through. So I don't think it set us back too much. I think what it showed us really was what the limitations, it really firmed up what the limitations were of the methods and tools we were using at the time, really.
Yeah, and I mean, I always describe it as one of the greatest recoveries of a spacecraft of all time. I mean, the solution to balance it using the light pressure from it's genius, and still it's the most prolific planet hunter. And yet, now I'm sort of using this as a setup because the next machine that can maybe get us to that Earth 2.0 is the one that you're directly involved with, and that's Plato. So give people sort of a background of what Plato is.
Sure. So I like to describe Plato as sort of a mix of some of the ideas from Kepler and some of the ideas from TESS. So from Kepler, we take the idea that you need to stare at one piece of sky for a fairly long time. And you want to stare at as big a piece of sky as you can. And in our case, that field is several times the size of the one that Kepler looked at. From TESS, we've taken the concept of using multiple cameras. And I say we've taken that from TESS. It's also a concept that was used for a lot of those early ground-based projects as well, where they had multiple cameras looking at very close but slightly different parts of the sky, so you could get an even bigger field of view. And
I love some of those missions with a whole bunch of almost consumer grade lenses attached to high-end sensors that are scanning just many degrees of the sky all at the same time. I think it's a really interesting way to approach the problem. So you've adopted that for Plato as well.
Yeah, but we've sort of taken it to a slightly ludicrous conclusion, because I think Super Wasp from the ground-based projects had the most on any mount, and that had 8 per telescope mount. Plato has 26 cameras on it. We have 24 what we refer to as normal cameras, and then we've got 2 fast cameras that just observe at a faster cadence, so they take images more quickly. But those 24, we've adopted sort of an extension of that idea of using the cameras to point at slightly overlapping but distinct fields. So those 24 are grouped together into 4 groups of 6. Within each group, they're all staring at the same piece of sky. So you have some nice redundancy there in case one of them goes wrong. But each of the groups is slightly offset from each other. So that's where you get the big overlap.
And so by having them overlap, they're acting a bit like a telescope of a larger aperture, adding together the data from the different images.
Exactly. Yeah, exactly.
But you are reducing your field of view. I mean, you could have them all pointing at completely different directions and get a much larger field of view with less redundancy.
Yeah, we could do. We certainly could do. And the reason we haven't gone completely distinct is, there's a few different reasons. The first, I mentioned redundancy. So within the groups, if you've got one camera that breaks or one CCD chip that breaks, then you've still got 5 more to look at the same stars. But also having those 6 cameras looking at the same piece of sky, you can average together the data from those 6 cameras to help reduce the photometric noise, reduce the random noise in your data. So you get a better quality light curve from a smaller telescope.
So are 6 separate telescopes working together for that data reduction better than one telescope that is the equivalent of the 6 together?
Yep. Yes.
Yeah. And cheaper. Like I think,
and a lot cheaper.
I think that was the discovery made with WASP and Super WASP was that if you want a big telescope, put a bunch of small telescopes together,
Yep.
and you've it's a tenth the price, and or I don't know what the price, what the price is,
Yeah.
and actually gives you redundancy and more aperture for the buck.
Yeah, because you can do then things with your optics to maximize the angle for your field of view. So even though you've got a small aperture telescope and a small mirror, or lenses in our case, you've got that big field of view that with a mirror the size of Kepler's is much harder to get. So yeah, it's taking those lessons learned.
But I mean, we don't see, say, the extremely large telescope being built out of 1,000 6-inch telescopes. So where does that trade-off switch the other way, where just bigger mirror is better?
It depends really on the science case you want to do. So the thing with all of these exoplanet surveys is one of the key parameters that you're trying to maximize is the number of stars you can observe simultaneously. Because the more stars you can observe simultaneously, the more likely the higher the likelihood that you're going to observe a transit at any time around one of them. Whereas when you get to something like the extremely large telescope, it's much more of a directed individual object or very small field of view science case where you focus in on a particular cluster or a particular galaxy or a particular pair of stars. So it's a much more focused, high powered instrument. So it just depends really on what it is you're trying to maximize.
Yeah, I mean, you're going to find the planets, but you're not going to be directly observing them.
No, exactly.
Yeah. Okay. So then you've got these cameras set up, and then what field of view has been chosen as the target?
So we're going to have two. We're going to have one in the southern hemisphere, one in the northern hemisphere. They're both overlapping with the TESS continuous viewing zones, the northern and southern ones, because again, taking lessons learned from Kepler, you want the longest baseline in time you can get. So we'll take advantage of the fact that TESS has already got these year-long chunks of data that we can sort of attach onto.
And I think for people who don't sort of know what we're talking about here, that TESS is sort of switching every month to a new location, but at the very North Pole and the very South Pole, its images are overlapping, and so it's always taking data on those two regions, and so
exactly.
for everything else, you've got 1 month at a time, and then for the North and South Pole, you've got half of the observing time for each one of them, and you're picking one then the other.
Yes. So those nice year-long continuous stares from TESS's end camera fit into part of our bigger field that we'll observe. So the southern field has been announced. You can find the coordinates for it online on the ESA website. So if anyone's interested in looking at where we're going to point the telescope, they can go and have a look.
And so because you've got all that data with TESS, you're going to be able to calibrate on, can it find the same planets that TESS was able to find and then some?
Yes, exactly. So we should, or Plato should be able to find anything that TESS has already found. And then because of the longer duration and the characteristics of the cameras, we should then also be able to find planets that TESS hasn't been able to find.
Right. So let's talk about the duration. So you're doing is it just a straight 6 months of observation, or are you switching back and forth between north and south?
It's 2 years on the south and then 2 years on the north.
Oh, okay.
And then
2 years.
2 years. Yep. So that's where we take that lesson from Kepler, because Kepler had 4 years on one field. We want to split our time to get more stars, so we'll take 2 years on each.
And then, assuming the mission keeps going, then you just switch back and forth between the two fields.
But yeah, that's one option. We'll see whether we get an extension. Fingers crossed. And if we do, we'll know partway through those 4 years, so we can then adjust what we're doing to either stay slightly longer on the first one or switch to the second one as planned and then spend slightly longer there. There's a few different ways we could do it.
So then with 2 years, I mean, we're back to an Earth-like world orbiting around a sun-like star, that's the kind of thing that you'll see 2 transits within 2 years.
Yep.
So what are you hoping to see?
So we are really pushing, and the whole mission's really been designed to find this Earth-Sun analog. So I was talking earlier about the cameras with their overlapping fields of view, and how having 6 cameras helped you reduce the noise down to get better quality data. In the very center of our field of view, you don't just have 6 cameras, you have all 24 cameras looking at the same patch of sky. So the stars in there will have the best quality data we can get. It's going to be better quality than TESS. The stars will be slightly brighter than the ones TESS can observe. And so we're really designed to push the transits, the transit depth as shallow as we can to get them. So what we're hoping is that we'll see a really shallow transit that lasts a very long time, that indicates a nice habitable zone, orbital period around something, a star. It's kind of similar to the sun, that we can then put the other part of Plato's data and analysis onto, which is all the stellar signs that we've got built into the mission as well.
When you say a shallow transit, what do you mean?
So the smaller the planet, the less light it blocks when it transits. And so the change in the brightness of the star is less. And so you'll see what we call a shallower signal. So the classic transit shape, when you plot out the brightness of the star on a graph, gives you a nice sort of U-shaped dip over time. And the depth of that U-shape tells you roughly how big the planet is compared to the star. So what we want is a nice shallow U-shape that's nice and broad, that gives you the long period and the small planet.
Right. And I mean, it's, when you think about it, like you might see one, and then a year later you might see another, and if you're really lucky, on just at the very end of year 2, you'll see it a third time and get your confirmation.
Yeah. So this is one of the big challenges, and one of the things that we've been spending quite a lot of time thinking about, actually. And this is another place where Plato differs from both Kepler and TESS. So with Kepler, we had the problem where the stars were too faint, really, for us to then do all the traditional ground-based observations with radial velocities to measure the spectrum, or measure the spectrum of the star to get the radial velocity to then measure the mass of the planet, or any kind of imaging to try and check that there weren't other stars there pretending to be a planet. And you couldn't really do most of that with Kepler, just because the stars were too faint to be able to get good data. TESS looks at brighter stars, and so we can do all of that, which is why with TESS we get nice confirmed planets with radii and masses. And so Plato, again, we're looking at bright stars, so we can do the follow-up. But unlike TESS, where the follow-up is left to the wider astrophysics research community, in Plato we do it within the mission for our best targets. So we will be following up the candidates that we find. And so one of the things we've been thinking about carefully is, well, if we see, like you mentioned, if we see one of these really interesting, exciting transits within the sort of first 6 months, first 9 months of the mission, and we know we're only going to get one more, do we start trying to follow it up straight away rather than waiting a year?
How do you follow it up?
So if you know, you'll know which star it is, and you'll have an estimate of how large the planet, if it's real, will be based on the transit that Plato itself observes. And so what we have is a group within Plato that is analyzing the Plato data to get those predictions, and then you send someone, or someone looks at it and says, that looks really exciting, and then it's given to our follow-up group, who give the coordinates to one of their observers, at somewhere like the VLT or the HARPS instrument, which is at one of the other observatories in Chile, and you take some spectral observations of the star. So you measure the star spectrum, and then you try and measure the radial velocity of the star from the spectrum. So how fast it's moving through space. And then if there's a planet there, over time, you will gradually see that radial velocity of the star change because of the gravitational influence of the planet.
Right. Okay. So, yeah. I mean the because I was sort of thinking if you're going to try and do a follow up, then you'd have to wait for the next transit. That's your follow up, but you don't really know when the next transit is going to happen, and it's kind of mean to say we need the VLT for a year. Just focus on our star.
Yeah.
Let us know when you see the dip.
Yeah. Exactly.
But you're saying that from the characteristics of that transit, the shallow transit, as you said, you're going to know whether it's a potentially interesting exoplanet, and there's a ton of observations that you can then begin making in preparation for, you can calculate the radial velocity, but also in preparation for when it actually does that second transit. Exactly. You're ready with a lot more information.
Exactly, Fraser. Yeah. So if something looks really exciting, we want to get started on those extra observations as soon as we can, because you're right. If we have to wait for a year, then we're a year behind that we could have been taking stuff.
Can you get any kind of estimate for when you think it might transit again based on the size, the shallowness of the transit and the duration that it takes for that transit?
Yeah. So if you have to make some assumptions as usual, but if you assume that the planet's orbit is circular, then you can get an estimate of its orbital period, from the duration of the transit. And so there'll be really big error bars on that estimate, but it gives you something to work with. And so you can then start to plan ahead for when you think the next transit might be. And if you're confident enough to start on the radial velocity observations, then as you go along, those will help you to refine that period if you start to see the signal in the radial velocities as well.
Now, I know that with a lot of the brighter objects, the hot Jupiters and stuff, you get actually multiple opportunities to observe the interactions between the planet and the star. You see it when it's passing in front, but you also get two when it's going behind, one when it goes behind and one when it appears. I mean, and that's great for observing atmospheres and stuff. Would you be able to detect some of those additional passes behind the star in your data?
For hot Jupiters, gas giants, yes, but certainly we should be able to. For an Earth-like planet, it's going to be tough, I think, still, because the primary transit when the planet passes in front of the star is so shallow anyway that when you get the occultation of the planet going behind the star, that's going to be really difficult to detect, I think.
Right. Yeah. Yeah. I mean, you get the drop in and to give people a sense, like when an Earth-sized world is passing in front of a sun-like star at the distance at, say, 1 astronomical unit, how much of a drop in brightness are you seeing on the star?
Hang on. So it's 0.1 of a percent.
Right. 0.1%. Yeah. So
it's something like that.
Right. So like what is that? Was it a thousandth?
Yeah.
10,000th? Anyway, we're off by an order of magnitude here, but it doesn't matter. The point is it's not very much
less than a percent.
Right. So a big issue that's people are really starting to understand is the amount of variability of the star. Like one of the big side effects of TESS was to actually measure variability in stars at a level of precision that's never been seen before. How are you accounting for this? Because you could wipe out a planet observation with a big sunspot.
Yep. Yes, you're nicely picking up on all the big problems. So variability is certainly one of our major concerns for the Earth-like planets particularly. And so what we have is a few different ways we can try and limit the effect of that. So the first is that, as well as the planet hunting side of the mission, there's also a stellar science side of the mission. So again, slightly differently to TESS and Kepler, we have sort of these two halves of Plato working together to do the best we can to learn about the planets and stars. And so we have, as well as searching the Plato data for planetary transits, we have a team who are analyzing that data using astroseismology and various other stellar science analysis techniques to both measure the mass and radius and age of the star, but also to characterize things like its rotation periods and its level of activity. And so we will learn as much as we possibly can about the activity level of the stars that we're observing as we go along. So that helps a little bit, because if we know how active the star is, if we have numbers to put on to sort of characterize the level of activity, we can feed those into then the analysis for the planetary side of things and try and adjust our searches to account for that. We are also able, thanks again to that sort of test calibration and the existing data, to see how active the star has been in the past, which isn't always a good indicator, but you can see how much the brightness of the star intrinsically varies over time. And so we can get an idea there as well of how much we need to account for when we're doing our search. There are also people within the planetary analysis side of things who have been developing methods to filter out that variability or to account for it as part of the search for the transits, so that you can adjust what you're looking for to account for that variation from variability.
Now, you have, I'm assuming, done simulations. You've looked at test data, calculated how many interesting planets TESS has found. You know what Kepler saw. So based on your expectations, what do you think we'll find and when with Plato, say in its primary mission? What will be the haul? How many Pokemons will you have collected?
So yeah, we have done run some numbers on that. We are expecting around 50 planets the size of Earth, or up to a couple of times the size of Earth, at various orbital periods. So that's not just habitable zone ones, that's across the whole period range. So if we're thinking sort of true Earth-Sun equivalents, then we're looking at maybe a couple of dozen, hopefully.
Wow.
Now,
but still, like a couple of dozen more than we know of already.
Yeah. Now, we sort of obviously don't know whether we'll get those in the first couple of years or the second couple of years, and because of those orbital periods, those year-long periods, it's going to take us a while to figure them out. As you've already mentioned, the time it takes to just get the transits, but then to get the follow-up radial velocity, and then to be really confident that what we found is really an Earth-Sun equivalent.
Yeah.
Then it's going to take a long time.
Right. And I think we go with, let's say first detection, and then you make a second detection and you've got a candidate, and then you make a third detection and then you're confirmed. But I think a second detection, that's news when you catch the second one. Yeah. So I want to sort of manage people's expectations here. Give them the timeline from when Plato launches to, let's say it makes its first detection within its first year, it then makes that second year, makes another detection, and we get a candidate second Earth.
Yep.
When people can mark their calendars now about when they should be expecting this to happen.
Sure. So at the moment, we're planned to launch at the end of 2026. Then we fly out to L2, which is the same piece of space that JWST is at. So we need to get there. We have to do the commissioning, flight calibration, make sure everything's working properly. That's supposed to take 3 months. So that's, by the time you do that, we're sort of at spring 27. So then let's say we find an exciting transit within the first 6 months. So by the end of 27, we have to process all the data. So mid 28, add another year. So probably in terms of the most exciting stuff, I don't think we'll see anything that we'll be confident about until 2029.
Right.
Probably.
Right. But there's nothing else. Like, unless someone really lucks out with, I don't know, something like, was it Speculus?
Mm-hmm.
Like the one that found the TRAPPIST, or the stuff you've been working on with Super WASP.
Yeah.
Nothing else can find this planet.
No, I think it'll be really interesting to see what TESS is able to do in the coming years.
Yes.
I mean, TESS has been an absolutely fantastic mission. I was at their science conference last week, and it's really exciting to see how many new results that mission is still producing, and that there's no sign of it stopping either. So I think it's going to be interesting to see how the next extension to TESS pushes what it's able to do. They're not sure what they want to do in terms of observing strategy yet. So there's a chance they could find something still, but they do have this disadvantage of only observing pieces of sky for a month at a time.
Right. Like, unless it happens to be in that northern patch or the southern patch, the chances of them finding it, looking at the right place at the right time for 2 years in a row is, remote.
It's low. Yeah, exactly. Yeah. So no, there's not much else.
Yeah. Yeah. And I talk, and I interview the TESS people, they say, yeah, the chances are incredibly small. I mean, maybe if it's a TRAPPIST one, like if there's something that just happens to be in the right location, that's really bright, the transit is really solid, the star is not that variable, maybe, but don't count on it, that there's too many other interesting planets. And so really, this is the expedition that has been sent out next after Kepler, learning from Kepler to go, okay, find the planet. And that first delivery of data shows up in 2029.
Well, yeah, for an Earth Sun equivalent, yeah. I mean, we should hopefully we will have done a good enough job that there'll be, interesting Jupiters and things like that coming out sooner. But the thing everyone wants to know, 2029, I reckon.
Okay, so I mean, obviously this is the thing that everyone is really focused on. Let's say that we do find the Earth-sized world orbiting around, or we find 12 of them, right? Maybe 4 years in, we've got a nice dozen of them. What can we do with that, with our current suite of telescopes and missions?
Yeah, that's where things start to get interesting, I think. So with what we currently have on the table, we can get radius, mass, age. So we can get bulk density, which already tells you quite a lot, and we can tell how old it is.
How old it is based on the age of the star.
Yeah, exactly.
And this, like, thanks to TESS with the astroseismology work, which is amazing.
Yep. And added to our own astroseismology work as well.
Yeah, but just this whole field. I mean, this is.
Sure.
Knowing the age of a star was always such a inexact science, and now thanks to astroseismology, the kind of work that's being done by TESS, and you'll be able that actually that age of the star problem has been much better solved.
Yeah, I mean, stellar ages is something I've done a little bit of work on in the past. And yes, without astroseismology, the methods we have are so imprecise and inaccurate that it's incredibly hard to get the age of any single star. And astroseismology has been a complete game changer on that.
Actually, for people who aren't sort of familiar with this revolution, because I don't think it has really been transmitted that far, but can you just explain how you determine the age of a star using astroseismology?
I can try. So the whole concept of seismology, astroseismology, is to look at the way that stars vibrate, essentially. So different stars vibrate in different ways. You can detect the frequency of the waves and the frequency of the vibrations by looking at the brightness of the star. And if you look for frequencies of changing brightness within that star's light curve, then you can see these frequencies showing up that indicate different oscillation and vibration modes. So the star might be pulsing inwards and outwards, or it might be pulsing up and down, or it might be doing multiple different pulses at the same time. And so measuring the frequency of those vibrations helps you to measure then the internal structure of the star. So you can get an idea of, by using the other information you have, you can get an idea for what the star looks like internally. And because stars change internally over the course of their life, depending on what type of star they are, then you can get some idea of their age from
that. And do you know what the sort of error margins are on this now?
We are pushing down to sort of 10% or better on the best ages now, which is incredible. When I was looking at stellar ages, you're looking at errors of about 50%. If you were lucky. So
So now you might know, like, if you see another sun, you'll know its age within, say, 500 million years.
Mm-hmm.
But in the olden days, you could say that star might be 1 billion years old, and it might be 8 billion years old. It might be 2 billion years old. It might be 7. It's crazy.
Exactly.
And the implications for planets around those two different kinds of stars are dramatically different. So I think. I've been absolutely fascinated by this story, and I don't think that people know this happened. And
no, it's not.
It has been very useful. Yeah.
No, I mean, as an exoplanet person, I feel that the exoplanets steal a lot of the limelight from Kepler and TESS, and even when we're talking about Plato as well. It's sort of it's an easier story to sell when you're talking about the planets and looking for another Earth, but the stellar science revolution has been almost as big and impactful.
You can observe sunspots on the far side of the sun by detecting the way the waves are moving through the sun. Activity that's on the far side of the sun. I think it's incredible. It's absolutely amazing. All right. Yeah. So we talked about sort of follow-ups, and so you're gonna you rightly pointed at first, we can measure all of these characteristics about the planet. We can measure things about the star. Mm-hmm. That's today. We can't observe it directly yet.
No, not yet.
So what other tools at our disposal that are coming online? I mean, we could potentially detect its magnetic field.
Ooh, I think magnetic field might be pushing too far. But I certainly think there are missions and projects in development where you could potentially start to take images of those planets. So you look at things like the very early ideas for the Habitable Worlds Observatory that are going around. You look at some of the other coronagraph designs that are floating around out there, where you basically put a blocker in front of the star and to block out its light, and then you can see much fainter objects close to it. Those kind of ideas are really interesting.
Yeah, I've done a whole series of interviews on the roadmap for building a coronagraph that would be capable of doing this, and the work
Yeah.
that's happening with the Roman telescope
Yep.
as sort of a first step, and then the various technologies that are being proposed to get you to the habitable worlds.
Mm.
But maybe the extremely large telescope is the next big machine that could potentially spot it.
I think trying to get an image of it from ELT will be a challenge. I think ELT potentially has the capability to do atmospheres. I haven't looked closely at how likely it is that ELT could do atmospheres of an Earth-like planet,
Mm.
but I think there's potential there to do it. And I think when you start to add that to the bulk density that you get from Plato, then you start to get into the territory of, well, what does this thing actually look like?
Now, there's the Ariel mission, which is
Mm.
another ESA mission that's coming up in 2028.
Yep.
Do you think it could give us more information about any of these planets?
Sadly, not about the Earths. So Ariel is a great mission. It's really interesting in the way it's designed and its goals, but it's very much looking at Jupiter-sized planets down to sort of Neptune-size planets. So it's looking more at the sort of bigger side of things. I think an Earth is going to be pretty much impossible for them to do,
Yeah.
sadly.
So now I want to step away from your specific role and responsibilities. I think anyone from ESA who's listening is absolutely knows that you are grateful for the incredible funding that's happened for Plato. How could it be better? So, what could be a better version of Plato? What could be the kind of king of all planet hunters? Do you think
Yeah.
if someone was willing to spend, say, Webb kind of money on a mission like this, what would it look like? Do you think?
Yeah. I think you would want to have multiple. I think you probably end up with something that looks like a cross between Plato and Ariel or Webb. So I think you have something that looks at not just the visible light, but also other wavelengths at the same time, or is able to get Plato quality data in different wavelengths.
So hold on. Like, doesn't that potentially mean that you only need one transit because you're detecting essentially both the dip in brightness and the presence of an atmosphere simultaneously?
Yes, potentially.
Wow.
So
So what would it take? That's
yeah,
interesting. Yeah, what would that take?
I think you'd need something with a lot more. I think it would be really hard to do with something of Plato's kind of design where you've got all the multiple telescopes, because you'd need to have the multiple telescopes for visible light and then the multiple telescopes for infrared or whatever other wavelength you wanted to aim at. And so suddenly you start to be building something that's got 100 telescopes on it, which is is just a little ludicrous. So I think
it's fine. This is a safe space. We can be
yeah,
ludicrous.
I mean,
So would you still go the multiple telescopes route versus the one big mirror with a wide field of view like Roman?
yeah, I don't know. Roman, I think is fascinating because it's such a different design, and it's still it's not compared to something like Tess or Plato, the field of view's relatively small, but compared to something like ELT, it's still pretty big. So yeah, maybe you take advantage of something like the Roman design, and accept that you're not going to get all of the many stars, hundreds of thousands of stars that you can do with a wide field of view, and just take tens of thousands instead.
Right. I mean, there is a second of those mission telescopes collecting dust somewhere at the National Reconnaissance Office, and it was offered to NASA.
Yep.
So maybe we've got the solution here. You build a version of Roman that is both taking, I guess, photometric data and spectral data
at the same time.
At the same time, and you're getting your one observation, and you're determining the presence of the planet just purely through the atmosphere.
Yes. Yeah, I think that being able to detect and do atmospheres simultaneously, I think, would be a big game changer. Because at the moment, you have to do the detection and then try and get the atmospheres later. But if you can get it all at once.
Do you know of anybody proposing this mission? I mean, this, I'm assuming you didn't just invent this today, but
I don't actually. I think, we're still at the really early stages of habitable worlds. And so it'll be interesting to see how that develops. But I don't think anyone's proposing, as far as I know, a joint detection atmospheres mission.
I mean, it's always this balance, because like on the one hand, things like TESS will drop thousands of exoplanets in your lap, but something like the Habitable Worlds Observatory will show you everything you want to know about one.
Yeah.
And if the one is really important, then that's also interesting in its own. In that case, it's quality over quantity. But there isn't a quantity successor to Plato proposed today.
Not today.
Yeah, interesting. Okay. So, David, what are you obsessed with?
At the moment, I'm obsessed with circumbinary planets, which are very cool. And I'm working with a PhD student to see if we can find any new ones in the TESS mission, because we don't know about many of this kind of planet. So anyone who's seen Star Wars has seen a circumbinary planet. It's the classic Tatooine planet where you have a binary star, and the planet, instead of going around one star, is going around both of them. And they're very rare. We know of 14 transiting ones. And so they're any new ones we can find are sort of, it's like going back to the early days of transiting exoplanets generally. If you can find one, you've already made a massive increase in your sample. And they're just fascinating things, because they're very weird, and we don't really fully understand all the constraints on them, and how they form or how they get there, and this kind of thing.
I mean, from the 14 that we know, are there some common threads about? I mean, I think about, like, you can only be so close to the stars, before it just gets too chaotic and the planets get thrown out or gobbled up by stars. But
yeah, so at the moment there seems to be some kind of inner limit, some multiple of the binary period where the planet any closer than that, and the planet, as you said, it's just too chaotic for it to survive. There also seems to be a limit on the orbital period of the binary itself as well. So if the binary is too short period, then it seems as though it's much more difficult for a planet to survive around there also, which sort of makes sense, because if you start to get the stars too close together, then they start sort of physically interacting as well as gravitationally, and so you start to get much more activity and flaring and ejections and all sorts. So there's some kind of binary limit as well. One of the things that I'm particularly interested in is whether all these circumbinaries are nicely aligned with the binary star, so whether, like in the solar system, they sort of all orbit in the same plane or not. Now, all the transiting ones seem to. They have to sort of cross the binary, the stars at some point to transit. But what we don't know yet is whether we're only finding aligned ones, and we just haven't found any ones sort of tilted over at weird angles, or whether they just don't exist. We just don't know yet.
I mean, I know that polar exoplanets have been found, which is a bit of tricky work because you have to calculate the rotation of the star and then figure out the rotation of the orbit of the planet. So do you think that the way the two stars orbiting around each other would draw a planet back into their orbital plane, or does it feel possible?
Yeah, I think that certainly seems likely at the moment. And the other thing is going to be just the formation mechanism from the disk, probably or possibly being more likely to be nicely aligned. Although, we have counterexamples of that where you have a disk around a binary star that's at sort of polar inclination. So it's always the exceptions, I think, that are interesting here.
There was a paper that I reported on this week about not a circumbinary, but I don't know what the term is, where you've got a binary star, but both have planetary systems around them, and they're separated. A wide binary, anyway. And ALMA observations of protoplanetary disks around both of the stars that are in orbit around each other.
Yeah.
Has anyone found a protoplanetary disk around a circumbinary?
Yes. I want to say yes, that we've seen protoplanetary disks around binary stars. I can't.
But specifically where the disk is around, like the two stars are orbiting, and then the disk is wider and around both of them, which is what gets you your Tatooines, right?
Yep. Yeah.
Yeah.
We know some of those. Yeah.
And so I wonder, you would. That would be the thing that would show you the orientation, because you would actually see the disk with ALMA, and then the stars going in some other orientation. And I wonder, but I'm assuming that has not been seen yet.
Not that I know of. Although, I'd have to.
I'll do a literature search after this. Yeah. Well, David, it's an absolute pleasure to talk to you, and I hope people, there's some memes going around on my channel about the kind of missions that I bring up again and again and again. And I talk about Tess, and I talk about Gaia, and I talk about Vera Rubin. But Plato is people need to add another slot to their bingo card, because I'm going to start going on and on and on about Plato as we get closer and closer to launch. A lot of our hopes and dreams are resting. Has it got good reaction wheels?
Yes. Yes, it does.
Good. Thank you for your time, and good luck finding Earth 2.0. I hope you enjoyed that conversation with Dr. David Brown. I'm going to give you some more thoughts in a second, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, David Giltonan, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, Spiderswap.io, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. When Kepler failed its primary mission, I was heartbroken, because like most of you, many of you, this is the dream, the other Earth, the science fiction future that we were always hoping, that for the longest time was just in our stories and in our TV shows and in our movies. And yet this was the mission that would have found it. And then it wasn't able to. And we've had to sort of think about planets around red dwarf stars. But we want to find that other Earth. And so Plato is the one that's going to do it. And I think it's so interesting that we're going to go from the time before, when we don't know how many other Earths are out there. We don't have a sense of just how many terrestrial planets orbit around sun-like stars within the habitable zone and so on. And then there will be a time after, when we do know, when we know what roughly the percentages are, that we can look out into our galaxy and count the number of planets and estimate with pretty good accuracy how many Earths there are in our galaxy and in the universe. I can't wait. And we're only just a few years away. All right. We'll see you next time.